There's an old spacecraft hurtling away from us right now, and on November 5th, 2018, it crossed a line that nothing built by humans had crossed twice before. Less than a single day of travel time took it from one environment into another. One side was the bubble our star built. The other side was not. That bubble is the thing that makes life on Earth even possible. The slow, invisible shield that protects every cell in your body from being torn apart by particles traveling at nearly the speed of light. The spacecraft crossed that line, and what it found on the other side was so different from what every model had predicted that 5 separate teams of scientists felt they had to publish 5 separate research papers on the same day, 1 year after the crossing, to explain what they had seen. This is not a mystery. It is something stranger. It is the realization that we had been wrong about something for decades, and that the wrongness goes home, all the way home, to the air we breathe. This is the hidden story of Voyager 2 at the edge of our solar system. Welcome back to Proof, where we uncover the hidden truths of the cosmos. If you are new here, hit subscribe now, because the story you're about to hear is the kind most people never hear about. Let us start at the very beginning, because to understand what Voyager 2 found at the edge of our solar system, you first have to understand what the edge of our solar system actually is. Most people, if you ask them, would say the solar system ends somewhere around Pluto. That is the picture we grew up with. Textbook diagrams put the planets in a neat row, then Pluto at the far end, then a fuzzy line, then nothing. Pluto feels like the boundary because we learned it that way. But Pluto is not the edge, not even close. Pluto orbits the sun, like everything else. It lives inside a region that is still completely dominated by our star. The real edge of the solar system, the line where the sun's influence genuinely stops and something else begins, is a different kind of structure, and it is much, much further away. To see why, you have to picture something about our sun you might not have thought about. The sun is not only light and heat, the sun is also wind. A real, physical, continuous wind blowing outward in every direction at the same time. That wind is made of charged particles, tiny bits of matter with an electric charge. They are mostly protons and electrons, the same stuff inside every atom. They stream away from the sun at hundreds of kilometers per second. That wind inflates an enormous bubble around our entire planetary system. That bubble has a name. Scientists call it the heliosphere. Helios means sun. Sphere means bubble. So the heliosphere is the sun's bubble. Inside the heliosphere, the sun's magnetic field is the boss. Inside the heliosphere, the solar wind is the main particle environment. Inside the heliosphere, everything from Mercury to the Moon to Mars to Jupiter to Saturn to Uranus to Neptune to Pluto, and far past Pluto, lives inside one continuous stream of material that came from our star. The outer edge of that bubble is called the heliopause. The heliopause is where the solar wind finally runs out of energy. It has been pushing outward for years, light years. And finally, far past Pluto, the pressure of the interstellar medium pressing back from outside becomes stronger than the sun's push. The wind stops. Beyond that point, there is no more solar wind. Beyond that point, the magnetic field environment belongs to the galaxy, not to the sun. Beyond that point, the particles are not solar particles. They are particles that came from somewhere else in the Milky Way. Crossing the heliopause is leaving the bubble our star built and entering the galaxy itself. It took Voyager 2 41 years to reach that line. The spacecraft launched in August 1977. It swung past Jupiter in 1979, past Saturn in 1981, past Uranus in 1986, past Neptune in 1989, and then it kept going. For 3 more decades, it drifted outward, gradually slowing because the sun's gravity still tugged on it, but still moving fast enough, more than 40,000 kilometers per hour at certain points, to keep making real progress toward the outer edge of the heliosphere. And on November 5th, 2018, its instruments recorded something very quiet, very clean, very final. The solar wind plasma reading dropped to essentially 0. Galactic cosmic rays spiked sharply. The magnetic field environment changed character. In less than 1 day of travel time, Voyager 2 had stepped out of the sun's bubble and into the real galaxy. It became only the 2nd spacecraft in human history to reach interstellar space. Drop a comment right now and tell me where in the world you are watching from. I read every single one. The first was Voyager 1, which crossed the heliopause in August 2012 from a different part of the sky. But here is where the story turns into something that matters more than that big milestone. Voyager 2 crossed the heliopause with something Voyager 1 did not have, a working plasma instrument. When Voyager 1 reached its heliopause crossing in 2012, its plasma science instrument, the device specifically designed to measure the plasma it was moving through, had been dead since 1980. It had been off for 32 years by the time of the crossing. Scientists had to pull everything they could from the magnetometer, the cosmic ray detectors, the other instruments. They learned a great deal, but the most direct window into the plasma itself on both sides of the boundary was sealed shut. Voyager 2's plasma instrument was still working. After 41 years in deep space in the radiation environment of the outer solar system, the instrument that the original mission team had built in the 1970s was still sending back good data. By any honest standard, that was almost miraculous. So, for the first time in history, scientists had a spacecraft crossing the heliopause with a working plasma instrument, capable of directly measuring the temperature, density, and speed of the plasma on both sides of the boundary, in real time as the crossing happened. That single fact changes the rest of the story, because everything that followed came from that single working instrument. The first surprise from that crossing came from the heliopause itself. For decades, the theoretical models of the heliosphere had been telling scientists to expect this. The models said the boundary between the solar wind and the interstellar medium would be a broad, gradual transition zone. The solar wind was expected to slow down and thin out over a significant distance before giving way to interstellar plasma. The two environments were expected to blend together over an extended region, like two rivers meeting and slowly merging, rather than two rivers colliding at a sharp edge. Voyager 2's plasma instrument recorded something dramatically different. The crossing happened in less than 1 day. On November 4th, 2018, Voyager 2 was sitting in the heliosheath, which is the outermost layer of the heliosphere, the slow, turbulent zone right at the edge of the bubble. On November 5th, it was sitting in the interstellar medium. The transition between those two environments was not a gradual fade. At the scale the instrument could measure, it was a sharp line. Voyager 2 went from one environment into the other in roughly the time it takes you to commute to work. The plasma on one side of the line belonged unmistakably to the Sun. The plasma on the other side belonged unmistakably to the galaxy. The research paper that described the plasma instrument's findings, published in Nature Astronomy in November 2019, put the width of the actual heliopause transition layer at less than 6/100ths of an astronomical unit. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the actual transition was less than 6% of that distance. At the scale of space physics, where distances are usually measured in millions and billions of miles, 6/100ths of an astronomical unit is extraordinarily thin. The models had not predicted a boundary that sharp. The second surprise came from the temperature of the interstellar plasma on the other side. The theoretical models had predicted that the interstellar medium near the heliopause would be cold, calmer, quieter. The temperature they expected was significantly lower than what the plasma instrument on Voyager 2 actually measured. The interstellar plasma outside the heliopause was hotter than the model said it should be. Not dramatically hotter in absolute terms, but measurably and significantly hotter in the specific sense of not matching what decades of theoretical work had predicted. The same paper noted that the very local interstellar medium near the heliopause is not uniform. Its properties change as you move through it. The quiet, cold, uniform void that the models described was neither as cold nor as uniform as the older pictures had assumed. The third finding came from the magnetometer data, which was published in a separate Nature Astronomy paper. Just inside the heliopause, in the outer heliosheath, the magnetic instrument detected what researchers describe as a magnetic barrier, a zone where the magnetic field intensity jumps sharply above the typical heliosheath values, forming a layer of elevated magnetic pressure between the bulk of the heliosphere and the interstellar medium. The idea of a magnetic barrier had been partially suggested by Voyager 1's magnetometer during its 2012 crossing, but Voyager 2 confirmed it more clearly and added detail about the role it plays in blocking cosmic rays coming into the heliosphere from the interstellar side. Cosmic rays are among the most energetic particles in the universe. They are produced when massive stars explode as supernovae, when supermassive black holes blaze at the centers of galaxies, and during other violent events across the Milky Way. They stream through interstellar space almost at the speed of light. Without the heliosphere to deflect and slow them, the inner solar system would be exposed to much higher intensities of cosmic radiation than we are now. The mechanism of that shielding, we now know, involves the magnetic barrier that Voyager 2 detected. The magnetic pressure of the barrier impedes the inward flow of cosmic rays, deflecting or slowing them before they can penetrate deeper into the heliosphere. That is a real measurable effect with real consequences for the radiation environment of the inner solar system, including Earth. The details of how the magnetic barrier actually works were not correctly described by any model built before Voyager 2 crossed through it. The fourth finding was the one that required comparing what Voyager 2 measured with what Voyager 1 had measured 6 years earlier, and it produced what may be the most conceptually significant result of the entire crossing. The two probes crossed the heliopause at different places. They were heading in different directions relative to the orientation of our solar system in the galaxy. Voyager 1 crossed in the northern hemisphere of the solar system, heading in the direction our sun is moving through the galaxy, toward the nose of the heliosphere, where the solar wind pushes hardest against the interstellar medium pressing back. Voyager 2 crossed in the southern solar system hemisphere, heading more toward the flank, a different part of the surface of the bubble. If the heliosphere were a symmetric sphere with the same properties in every direction, Both crossings should have found essentially similar conditions at the heliopause. They did not. Voyager 2 encountered a thinner boundary than Voyager 1 had encountered, with stronger interstellar magnetic fields and different plasma conditions. Both probes found the heliopause at roughly the same distance from the Sun, about 120 astronomical units, which was itself somewhat surprising given that the two crossings happened under different conditions of solar activity. But the character of the boundary itself differed between the two locations. The heliosphere is not a perfect sphere. It has a shape and a symmetry determined by the direction the Sun is moving through the galaxy, and by the way the interstellar medium flows around it. The two Voyager crossings, at different points of this asymmetric surface, measured different things because the surface itself is different in different places. That asymmetry matters because if the heliosphere is compressed on one side and extended on the other, then the thickness and strength of the protective barrier it provides against cosmic radiation also varies depending on direction. The inner solar system is not equally shielded in every direction. The amount of cosmic radiation reaching Earth from different parts of the sky may be subtly influenced by the shape of the heliosphere itself. The fifth major finding concerned what the interstellar magnetic field was actually doing near the heliopause. For decades before either Voyager spacecraft reached the boundary, physicists had predicted that the galactic magnetic field outside the heliosphere and the solar magnetic field inside the heliosphere would be largely disconnected. Two distinct magnetic environments, separated at the heliopause, with limited interaction between them. What both Voyager 1 and Voyager 2 found at the boundary was a more complicated picture. The galactic magnetic field outside the heliosphere is stronger than expected. It runs 2 to 3 times the intensity that the best pre-crossing models had predicted. That stronger field exerts significantly more pressure on the heliosphere than anyone had calculated. Independent estimates based on the Voyager data have suggested that interstellar particles pressing against the heliosphere from outside exert up to about 10 times the pressure that previous models had assumed they did. That is not an abstract number. The pressure the interstellar medium exerts on the heliosphere helps set the size and shape of the heliosphere. A more compressed heliosphere might provide somewhat less shielding to the inner solar system. Over geological timescales, the Sun moves through different regions of the galaxy, and the local interstellar environment changes around it. If the Sun were to pass through a region of denser or more magnetically active interstellar medium in some future era, the heliosphere could be compressed significantly enough to expose the inner solar system to higher cosmic ray intensities than we currently experience. The Voyager data does not prove that this has happened or will happen on any specific timeline. What it establishes is that the interstellar medium exerts more force on the heliosphere than the models accounted for, and that changes the baseline calculation for how stable and consistent the heliosphere's protective properties actually are. All 5 of these findings were delivered to the scientific community on the same day, November 4th, 2019, 1 year after the crossing. 5 papers and 5 instruments published together in Nature Astronomy. The simultaneous publication was deliberate. The findings from the 5 different instrument teams on Voyager 2 were interconnected. Each one added context to the others. Publishing them together meant the broader scientific community could see the full picture at once, rather than assembling it piece by piece over months or years. Patrick Cohen, the Voyager program scientist at NASA headquarters in Washington, described Voyager 2 as the first platform to actually experience the interstellar medium from the inside, calling it, quite literally, a pathfinder. That word is chosen carefully, not because it sounds dramatic, because it is accurate. There was no path before. There were models built from observations taken from far inside the heliosphere and theoretical reasoning about what should be on the other side. Those models, for all the sophistication that went into them, missed the sharpness of the boundary, the temperature of the plasma, the intensity of the magnetic field, and the asymmetry of the heliosphere itself. A pathfinder is something that goes somewhere first and brings back information that changes the map. Voyager 2 is not coming back, but the information it sent home has changed every map that mattered. If hidden stories like this are why you come here, subscribe now, because we are just getting started. Now consider what this means for the 2 instruments Voyager 2 still has operating in interstellar space, more than 7 years after the crossing. The heliopause was not the end of the scientific story. It was the beginning of a new chapter. The interstellar medium that Voyager 2 entered on November 5th, 2018, is not a uniform quiet background. It has structure. It has turbulence. The plasma in it varies in density and temperature as the spacecraft moves through it. Compression waves from solar events, eruptions on the Sun, powerful enough to send shock waves all the way out past the heliopause and into interstellar space, have been detected by Voyager 2 from outside the heliosphere. Those detections have demonstrated that the 2 environments are connected in ways that go beyond the static boundary picture the pre-crossing models described. The heliosphere breathes, in a sense. It responds to solar activity into the interstellar medium pressing against it, and Voyager 2 has been measuring that breathing from the outside since late 2018. Each year that passes brings the spacecraft closer to the point where its power supply can no longer sustain its instruments. The team at NASA's Jet Propulsion Laboratory makes harder decisions each year about which instruments to keep running and which to power down. The plasma science instrument that made the heliopause crossing measurements so historically complete is still operating, but it is operating on a spacecraft that loses about 4 watts of power every year and that cannot last indefinitely. The window for direct plasma measurements from the southern interstellar medium is finite. When it closes, no replacement instrument is currently on a trajectory to fill that gap, and no mission to do so has been approved. What Voyager 2 crossed on November 5th, 2018, was the edge of everything our sun built, everything that exists within its protective influence, everything our civilization has ever called home in any physical sense. And on the other side of that edge, it found a universe that was hotter than expected, more magnetically active than predicted, pressing harder against our solar system than any model had calculated, bounded by a line thinner and sharper than anyone had anticipated. The simple textbook picture of the heliosphere, a smooth, symmetric sphere gradually fading into quiet, interstellar space, has been redrawn. 5 teams of scientists published 5 papers on the same day to begin that redrawing. And the spacecraft that made all of it possible is still out there, right now, still moving deeper into interstellar space, still measuring, still transmitting, still doing what it was built to do in the decade before most of the scientists currently studying its data were even born. Now go one layer deeper, because there is one specific finding from the crossing that matters more directly to you than the rest, and it is the one that took the longest to settle. The heliosphere is not just a diagram. It is the reason life on Earth has been able to proceed the way it has. Cosmic rays, the ultra-high energy particles produced by supernovae and other violent events throughout the galaxy, stream through interstellar space constantly. Without the heliosphere to partially deflect and slow them down, the inner solar system would be exposed to significantly higher cosmic ray intensities than we currently experience. Research has suggested that extended exposure to elevated cosmic ray levels could increase mutation rates in living organisms, could affect atmospheric chemistry, and could shift climate in subtle ways that cascade over millions of years. The question that the Voyager 2 data now raises, not loudly enough to cause alarm, but seriously enough that researchers are actively investigating it, concerns how stable that protection actually is. The answer depends on 2 variables. The first is the properties of the interstellar medium the heliosphere is embedded in. If the local interstellar medium is denser or more magnetically active than what surrounds us now, the heliosphere gets compressed, and a smaller heliosphere provides less shielding. The second variable is the sun's own activity, which sets how much solar wind the heliosphere has to work with. A more active sun produces more solar wind, which pushes the heliopause outward. A quieter sun produces less solar wind, which lets it move inward. What Voyager 2's crossing data established is that the interstellar magnetic pressure on the heliosphere is roughly 10 times greater than the pre-crossing models had assumed. That stronger external pressure means the heliosphere is being compressed more than the older models predicted. It is, in other words, somewhat smaller than those older models said it should be. This is not a crisis. The heliosphere is still more than large enough to provide substantial protection to the inner solar system. But it does mean that our models of how much protection we actually have and how that protection might shift over geological timescales as the sun moves through different regions of the galaxy need to be recalibrated against the real numbers. The only way to get those real numbers was to send a working plasma instrument through the boundary, which is what Voyager 2 finally did. That recalibration is still going on. Papers published since the 2019 crossing analysis have continued to refine the picture of the heliosphere's shape, its response to solar activity changes, and the structure of the very local interstellar medium that surrounds it. Each of those papers draws, in part, on Voyager 2's continuing data stream from inside interstellar space. Think about what that continuity really means. From November 2018 onward, Voyager 2 has been sending back measurements from inside the interstellar medium every single day. Plasma density readings, magnetic field strength and direction, energetic particle counts from both solar and galactic sources. The spacecraft is, in a real sense, drawing a map. Not a map of mountains and valleys the way a surface probe draws a map of a planet. A map of conditions. A record of what the interstellar medium near our solar system is like, as a function of distance from the heliopause, built point by point as the spacecraft moves deeper into it. No such map existed before November 5th, 2018. No telescope on Earth or in Earth orbit can substitute for it. The map can only be drawn as long as the spacecraft continues to operate. In 2023, there was a reminder of how thin that thread is. NASA sent an incorrect command of Voyager 2's orientation on July 24, 2023, and the spacecraft's antenna swung 2 degrees away from Earth. At a distance of more than 18 billion kilometers, that small misalignment meant that Voyager 2 could no longer receive commands and could not transmit scientific data back to Earth through its high-gain antenna. For roughly 14 days, the longest-lasting gap in the post-crossing data stream, the spacecraft was effectively mute. The only antenna on Earth capable of sending a command that might rescue the spacecraft was Deep Space Station 43, the 70-meter dish at Canberra in Australia. The dish needed to send what NASA called an interstellar shout, a tightly focused uplink aimed at Voyager 2 with the antenna pointed at the spacecraft's known coordinates. The shout, called a carrier wave-only command, was sent on August 4, 2023. It worked. Voyager 2 received it, reoriented its antenna back toward Earth, and resumed transmitting. 14 days of data points, lost forever. In the full context of a mission lasting decades, 14 missing data points is a small gap. But every gap in the record is a section of the map that cannot be filled in later, because the spacecraft only passes through each point in space once. Whatever conditions existed in that 14-day window, in that specific stretch of interstellar space, at that specific distance from the heliopause, were recorded by instruments that were not talking to anyone on Earth for those 2 weeks. That data is gone. The larger gap, when it finally arrives, will be permanent and total. When Voyager 2's power supply drops below the threshold needed to run even one instrument, the map stops where it stopped. Whatever lies further out in the very local interstellar medium will be unknown until something else reaches those distances. Nothing else is currently on its way there. There is one more aspect of what Voyager 2 found at the heliopause crossing that deserves to be here, because it shifts the story from physics back into something that is harder to define but equally real. Both Voyager 1 and Voyager 2 arrived at the heliopause at approximately the same distance from the Sun, roughly 120 astronomical units, despite having crossed at different times and under different conditions of solar activity. Scientists found this surprising. They expected the size of the heliosphere to vary meaningfully with the solar cycle, the roughly 11-year rhythm of rising and falling solar activity that drives sunspot counts and flare frequency. At solar maximum, more wind pushes the heliopause outward. At solar minimum, less wind lets it pull inward. Voyager 1 crossed during relatively low solar activity. Voyager 2 crossed during relatively high solar activity. The expectation was that they would find the heliopause at meaningfully different distances. They did not. That suggests the interstellar medium's pressure is stable enough over the relevant timescales to keep the heliopause at roughly the same location, regardless of where the Sun is in its activity cycle. The external environment, in other words, is more dominant in setting the heliosphere's size than the internal solar wind alone. The galaxy presses back, and it presses with enough consistency to hold the boundary nearly steady. There is something in that image, our Sun doing its best to maintain its bubble against the constant external pressure of the galaxy, pressing in from every direction. The galaxy pressing back hard enough to hold the boundary steady no matter what the Sun does internally. It is a relationship between our star and its galactic environment that our models had not described correctly, and that a 41-year-old spacecraft, still functioning on hardware built before home computers existed, measured directly for the first time on a November day in 2018. That spacecraft is further from Earth today than it was then. Its power supply is smaller, its instrument count is smaller, its remaining instruments are still collecting data from inside the interstellar medium, still building the map that begins at the heliopause crossing and extends outward into space that no model has correctly described from first principles, and no mission besides Voyager 2 itself has ever measured directly from within. If this is the kind of real, verified, world-changing science you came here for, subscribe now. Turn on notifications. Drop a comment telling us which finding from the Voyager 2 crossing surprised you the most. Share this with someone who should be watching, because this is the kind of story that deserves a much bigger audience than it gets. Thank you for watching. The cosmos is calling. Are you ready to explore?